Okay, so last time we met, we started looking at the sequence networks. Sequence networks are basically a special architecture or type of neural network that have this special property that they have a feedback from the output back into the inputs. That is the architectural difference. And that output, remember, when we look at a network, we can look at it from the standpoint of a layer, right? Or multiple layers. Okay. And so in a sequence network, you find that the output from the output layer is sent back and added to the input, to the inputs at the input layer. So that's what makes it unique. Now, this simple architectural introduction brings about some additional properties. One being that it has an idea of sequence. That is, it can tell the difference between, numbers or inputs rather that came in a particular sequence. So let's assume that the input, which is always going to be a vector or a matrix, if you include the batches or the batches. But let's just say a single sample. The input that comes in, let's represent it by simple numbers. So we can actually tell the difference between um, if you have inputs coming in as 5432, it will be able to differentiate between that one and 5342. It's the same set of inputs, right? But the order has changed. So it's able to understand sequences. That's why they are called sequence models. Then they also have this idea of history. They have an internal state that represents all of the previous inputs that have passed through them over time. And then um, also remember that when we talk about over time, what we are actually saying is that the inputs that you send to a sequence model, you send them in one at a time. That's why it is sequential. So you send each vector one at a time, each one at a time, right? You don't send all at once. And that's why they're also called sequence models, because they're sequential in nature in that sense, sequential in terms of how the inputs pass through. So even though sequence models, and in this specific case, recurrent neural network, you know, is actually a single um, layer like this, which you can represent by this small box. This small box actually contains, let's assume there is just a single layer in it, even though you could have more than one layer in it. But let's assume it has a single layer. And in that single layer, you have the X, which represents the input vector, right? That X input comes in. It goes through the normal processing that we've come to understand that happens inside a neural network, which is typically going to be the um, weighted sum, right? Plus the activation, and then an output comes out, right? Now, this output for recurrent neural networks, this output is called the hidden state. It's basically a representation of the accumulated history or state of what the that particular layer or that network has seen over time. But now you have some part of that output or that hidden state is sent back through um, a particular set of weights, which we call the hidden weights, WH, back into the input. And this input, it is added. So what that that does is to essentially give us this equation to represent it, that the hidden state is the hidden weight times the previous state. So you can now see that the current state depends on what inputs you saw before, because what inputs you saw before, right, is also part of the inputs that will determine the next state, in addition to current input. So is the hidden weight times the previous hidden state plus the X weight, which is the weight for the X, the actual input or the current input, times the current input. So it is now a sum of the two weighted sums. And then you pass that through this activation function, which is a than, and that gives you the hidden state. So then at the tail end, when you eventually want to extract the actual output, you take this hidden state and you multiply it by the output weight, which is WO, right? And you may pass it through an activation function, maybe a sigmoid or whatever, and that will give you your output. So that is how recurrent neural networks are. So another way of looking at that is, this is a typical way. If you look at a lot of books and research material, all the literature on recurrent neural networks, you see that it is unrolled. This is an unrolled version of this same thing. You can see that in this unrolled version, we don't have this loop from output back to input. Rather, you have each time step. So in the unrolling, each of these represents a time step, not really a layer per se. But of course, when the calculations are done, it will be calculated as if it is separate layers. So the V is essentially the hidden state in the previous time step, the hidden state in the previous time step. And as a summary again, as a recap, the training of these models uses BPTT. BPTT means back propagation through time. Back propagation through time. So that means you're essentially going to do back propagation, calculate the the gradient of the loss with respect to each layer, and then you use the chain rule to essentially propagate backwards to get the gradient at each previous time step. And then you now use that one to calculate. So that is kind of a recap. But one of the things that we talked about and we identified as a problem with the recurrent neural networks, the first architecture that follow this sequence model paradigm, is this problem of vanishing gradients. So why do we have this problem of vanishing gradients? Because if you want to now calculate gradients, remember you're using back propagation. Back propagation uses chain rule. Chain rule is essentially product of gradients from the previous layer, or from the current layer to the previous layer. So you keep on multiplying it backwards. That's what chain rule does. So because of that, I think there was a place where you see, yes, this is where you can see, this is actually the equation, derived equation for the back propagation through time. So back propagation through time, eventually you find that the partial derivative of the cost function with respect to each hidden state, right? In other words, the back propagate the the gradient essentially, the gradient for a particular time step is equal to the gradient of some reference time step, you know, I, ahead of that time step, times all the weights in between. That's what this means. So if, for example, we were to look at, let me see how I can explain this um this 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 equation, which is kind of a derivation of overall backpropagation. So what you are saying is that let's assume this is a particular time step, right? And then you have multiple time steps in between, right? So you have a reference time step, maybe where we started or where we ended. Well, it's always typically where we ended, because you are training these models by collecting data that was recorded over time, right? That's why it's sequential data. So let's assume each of these boxes represents a time step. So, and you have just that representation I showed earlier. So what we are now saying is this. Um, Now let's assume that the time step with the upper case T, right, represents the time step at the final point of training, right? Or at the final, data point. So this is like the output. This is the time step that corresponds to the output. And that's where we have T, okay? Then any of these other ones here can be the small t, which is at any time T, right? So what this means basically is that if this is the time step, I want to calculate the gradient, at this time step here, this time step little t. What I will do is take the gradient at time step big T, which is typically going to be exactly the gradient of the L, the output, right? The gradient at this point is typically going to be the gradient. It's basically going to be the gradient of the output, which is the L, right? The Y hat, right? Maybe not exactly Y hat though, right? It will be times a certain factor, not exactly Y hat, because um they this T is not the same as Y hat, but T is Y hat. Remember, T is Y hat times the weight, that will generate the outputs, then the sigmoid function. So it's actually going to be times the weight, of Y hat, which we can call it WT, the big T, right? Okay. Times a certain factor. That factor is brought about by the activation function. So I'm not going to go into that, but let's just say activation function prime, right? A prime. Or let me make it F prime because we typically just use F for the activation function. Okay. So it will be WT F prime, where F is the activation function. So essentially taking the gradient of the activation function, you multiply it by the weight, right? And then you multiply that by the gradient of the cost function with respect to the output, the predicted output. So that gives you this dl del L del HT. That is the essentially the gradient with respect to the outermost you know um, um, hidden states, right? So what this equation is telling us now is that for me to get out the gradient at this point, which is del L, right? Um, del HT, right? H small t here. Because remember, what we have in here is HT, H with a small t. And all this can also be T's as well. While this one is H with the uppercase T, which is a H at that point. So we are just going to take, during the back propagation phase, we're just going to multiply all of them backwards. So during back propagation, we'll take this original del H, this original one, and then we'll multiply it by the weights because there is weight here, and then we'll multiply it again by the weights here, and then we multiply by the weights here. So of course we are going backwards. All of this, that's what back prop is. That's a chain rule effectively. And then, so for each of the T's, right, between this small t and this. In other words, for each of the time steps, from this time step to this time step, if I want to get the actual gradient at this time step, I have to take the gradient at this ht, which is actually obtained by taking the gradient with respect to the actual prediction times the W. Okay, this should not be WT, this should be WO. I forgot that, please. That's the weights, the output weights, right? So this times this is actually what gives you the del L del T. Del L del T, del L del HT is actually del L del Y hat times um, WO times the gradient of the cost function. So everything is all about gradients. But you now keep multiplying it backwards through different time steps to this. That's why this symbol here is the same thing or is similar to a summation. The only difference is that summation was, we are saying, is sum of numbers in a series. But this one, this is uppercase letter pi in Greek. It's basically pi in Greek. Is product of numbers in a series. So it's going to be the product of all of the weights, right? Times this one. That's how you get that. So that's what this is. And you can easily see then how you can have the gradient shrinking. Because what's essentially happening is that let's assume that each of these W is a small number, because typically weights are small numbers. If you have trained neural networks and you look at their weights, you find that they have small numbers. Small numbers that are always typically less than 1, right? So if you have a number that is less than 1, 0.1, okay? Let's say this one is 0.1. Okay, that's this weight. Then you could also have other weights as well. And you will have a lot of them. So you can have another one here. This could be 0.2, for example, or 0.15, or 0.14, and so on and so forth. You just have small numbers like that until you have all of them, right? 0.3. This one could be another small number. Maybe this one will be 0.8. Even if they are still large, close to 1, but as long as they are less than 1. Okay. So let's assume that those are the weights, right? This weight is 0.1, this one 0.14, this one 0.3, and so on. So you are going to end up, right? To get this DL del L del HT is going to be 0.1, right? Times 0.14 times 0.3 times 0.8 times 0.5. And the one that is 0.5 is the width, the WO, which I didn't actually give a value here. But then, we can just give the value of 0.5, right? It's also a weight, but it's not a weight it's just a weight between the last hidden state and the final output. Okay, so imagine having this. If you were to take out a calculator and do this simple maths calculation here, you will see that this number becomes very, very small. It becomes very, very small. But let me just do it quickly so we can see. It becomes a very small number. And that is what we mean when we say vanishing gradients, right? That's what it is. That's what it is. It is small numbers. So this is going to give us a number that is relatively smaller, you know, um, is actually going to give us 0.00168. Okay. So this is for maybe about how many time steps? 1, 2, 3, 4. maybe 5 time steps, right? 5 time steps. So imagine you can now see that it grows as the time steps grow. And since the time step essentially represents the length of the sequence, or what we call the sequence length, then what you can see how the gradient will either vanish if the weight is less than 1, or it will explode. Because the other side of this is that if all of these numbers were higher than 1, then it will grow exponentially as well. Of course, you can ask a question, what if there is a mixture of numbers above 1 and numbers below 1? Yes, it will be stable. But then we're always trying to ensure that we consider the worst case scenario. You don't really have control over these numbers, right? So you have to think about the worst case scenario. And the worst case scenario is that you are going to either have vanishing gradients or exploding gradients. So whenever you hear that those words or those concepts, this is what it's actually referring to. The fact that because you're doing products across a very deep neural network, in this case, deep, not in terms of the number of layers, but deep in terms of the sequence length, the number of time steps, right? Then you will have a situation where the values become close to 0. And you now see that if the gradient comes very close to 0, then the parameter update. Remember, parameter update is previous parameter minus the learning rate times the gradient. Of course, this is for stochastic gradient descent. Others like Adam have momentum included and other things. So those ones are a bit more complex. But if we just go with a simple calculation using stochastic gradient descent or gradient descent, you can see that if you go and put a small learning rate, then it's even going to be lower. So parameters don't increase, especially at the earlier stages. Remember what we just did now, even though I have wiped it, but it means that the parameters at the beginning of the sequence, right? Um, the time steps at the beginning of the sequence will be much, much less, right? Even though these are all shared weights anyway, right? It's all shared weights, right? But you get to a point where the um, values of X, at the beginning will not have much, they'll lose their value, right? And so the impact of that in a sequence kind of problem, a sequence model is that the relationships, what it learns about the earlier parts of a sentence, for example, it forgets, especially if the sentence is so long. So at the tail end of the sentence, it cannot really correlate. For example, if you look at this sentence here, I grew up in France. Then if there's a whole lot of other words and sentences in between, before we now say I speak fluent dash, it will not be able to connect this dash to France because France happened very far away. But if it is close by, it will be able to come up with French, yes, because France, of course, if you grew up in France, then you can speak fluent French. So this is typically how it manifests. The fact that the relationships between concepts that are not close together are kind of lost due to this vanishing gradient or exploding gradient. So exploding gradient is the second problem. The biggest challenge with exploding gradient is that when you're training a model, the training is unstable. You have a lot of nans, like we have seen before, right? And then the weights begin to diverge. They never converge. So that's the biggest challenge that the recurrent neural network has. So the researchers solved that problem by coming up with the LSTM. The LSTM is a long, short-term memory. Unlike a recurrent neural network that only has one hidden state, right? And that hidden state is fed back as input, to the next time step, right? Then the output is obtained by applying some weight to the hidden state. So the output is not actually a state of its own, it's just a derivative of the hidden state. And this output is only at the final time step. But in LSTM, they introduced three gates, right? Now we're going to talk about the concept of a gate. In machine learning, especially in neural network design, we have what we call gates. A gate is a mechanism where you can use to switch off a signal that is coming in, switch off an input, or switch it on. It is basically off. That's why it's called a gate. And the way you normally achieve gating is by using an activation function that always has either 0 or 1 value, right? It doesn't have any value in between. But if you have values in between, that in between section is not really gating. It's more of attenuation, right? Attenuation is when you reduce the value by a factor, or amplification is when you increase the value by a factor. But what we want is gating. We either want the full signal to come through or none at all. So we typically do gating. If you remember our study of activation functions a little bit, there are a few activation functions that have that characteristic where they kind of suddenly switch from a very low value, right, to a very high value, right? And that point at which they switch, that's a switching point, that's a threshold, right? If you look at this, there are two main ones, if you remember, that have this characteristic. The first one is the hyperbolic fan, which we just saw. And then the second one is the sigmoid, right? The sigma is the first one we knew about. The main difference between the hyperbolic fan and the sigmoid, of course, is the actual values, right? The hyperbolic fan, the the lower value is -1, while the higher value is +1. For sigmoid, lower value is 0, while the higher value is 1. So that's the main difference. But there's also a difference in terms of the steepness of this section. The steepness of this transition section is what really makes a difference, right? Because we are talking about gating. You don't want a transition section that is um, flattish. You want a transition section that is sharp. So if you have a gating function and your gating function looks something like this, this is not really a gating function. This is not a gating function because this section here is not really it. There's a substantial part of the input here that is kind of still linearly changing with the output. It's not a direct 0 to 1 switch. This substantial section makes this not a good function for gating. But this one, you can see that the section where it has this linear behavior is much shorter, it's much smaller, and it's very highly unlikely that the actual values exist. The number of actual values that will exist, its range, it's very small. As a matter of fact, for a gating function, you keep on applying more steepness to this section up to a point that you could even say that you don't even get a very narrow transition section that is very narrow, something like this. So that's a gate function. And the best function for gating is the sigmoid function. That's why you are seeing sigmoid, elements here. So what the sigmoid basically does is that, yeah, it has a particular value here, which is a threshold. At this threshold value t on the x-axis, it is going to below that threshold t, right? The value for the output will always be 0. And above this threshold t, the value for this output is always going to be 1. Right? That is what gate function is. So with that now, you can now understand why we have so many of these sigmoid functions in the LSTM. We can now try to analyze what is going on inside this cell. There are 3 gates. You have the forget gate. The forget gate, of course, is a sigmoid function. The second gate is the input gate. Input gate is also a sigmoid function. Then you have the output gate. The output gate is also sigmoid. The LSTM uses a gated architecture, uses those three gates, the forget gate, the input gate, and the output gate. And these gates, right, have parameters. So the gates can actually learn, right? They are weights, actually, not just sigmoid function itself, but they are also weights. So the weight, it learns which signals to forget. So a signal that it wants to forget, that means no matter what comes in, it means it can adjust its threshold in such a way that the signal that it wants to forget will always be less than this threshold. So the value will always be zero. The output will always be zero, right? And for signals it wants to remember, it waits, for those particular signals to give those weights high values so that the eventual output that comes out high. So the forget gate gives the LSTM the opportunity to learn. They are learnable parameters behind it, right? And we'll see more details about it later. But the learnable parameters allow it to learn which signal to allow to go through and which signals it should essentially drop or block. So now, if you look at this, it still has the same XT and HT minus one that the LSTM has. In other words, the current input, that's the XT. Then the HT minus one, the previous internal state of the previous time step. Okay. Then on the output side, it also has the HT, which is the hidden state, right? That the RNN, the recurrent neural network, has. But it also has a cell state, a CT, which is the cell state. Unlike a recurrent neural network where the output was achieved by taking the hidden state and passing it through um, a weight and a gate function or sigmoid function here. But for the LSTM, the output is the hidden state is taken as the output direct. So you are training your model on the hidden state at the last time step, right? Then, because of that, the cell state is now decoupled from the hidden state. Here, the hidden state and the output were coupled together. So there wasn't too much room for learning, separating and learning. It's like you having, think of it like learning how to play a piano, for example, and you need to separate your hands. What that means basically is you need to be able to play on one hand separate, different from what you're playing on the other hand, right? But if your two hands are moving the same way, you cannot, the variety of what you can play is much less. But if you can separate your hands and play each separately, then the variety of things you can play are much more. That's the same kind of thing here. With RNN, the HT and the ZT were basically coupled because they are essentially the same thing. But here, CT is a totally new state, a new internal state that is introduced, and that's called cell state. I'll talk about the cell state more. And this cell state is what makes the difference in terms of counteracting the vanishing. So, so the cell state is kind of a continuous history through time. But for me, I always think of the cell state as equivalent to a skip connection when we're talking about residual neural networks and so on, right? The cell state continues to remain almost the same, without much change. So this is a cell state at time t minus one, okay? While this is a cell state at time t. And you could see that the cell state remains as a kind of uh, common factor that remains. That is what you are seeing here. You see that this cell, even though this is not a good drawing to represent that, in the next slide, you'll see something more represented. But the cell state, if you trace it, it starts from here. This is the previous CT minus one. It goes and it comes here and it just goes all the way out. So it's the same cell state. The only difference is that at this point, you see this dot, there is a product. So something is added to the cell state at this point. So what's actually happening there is that at that point, what is being added is the xt and ht minus 1, which is the sum, remember the weighted sum of the current input, the previous, the hidden states of the previous time step. They are added. And then, unlike a recurrent neural network, where when those two are added, it passes through a an activation function. Here it passes through a gating function. Now you may ask, okay, but are they not the same thing? Activation function, this is a sigmoid function. Here the same gating function, see a sigmoid function. Yes, they are the same, but they do two different things. Because they do two different things, there is there's a difference in behavior. The other thing is that here, this is just an activation function, but here there are weights that will be applied. There will be weights that will be applied so as to drop some of the inputs. So what's happening here then is that you now have the xt and ht minus 1. They'll come and they'll multiply. They'll come and multiply with what is in the cell state. This is a multiplication. That's why I see the dot. And then that adds up, right? And moves on. Then something else comes to add to it. So we'll do a breakdown of that. But something else also comes in and adds to it, right? That's something else. So this now adds to that cell state. That something else is going to be the input modulation, the amount of input that has been modulated. So you see that there are three sections to this whole thing, right? But at those three sections, one thing continues to remain constant or common. That is the cell state. The cell state C remains common, remains constant. If you look at it that way as C, a signal that continues to move through, but this signal gets modulated by other signals that come in, then that will allow you to understand this thing properly. Then the third thing that comes in, right? Well, it doesn't come in this time around, it goes out, right? The signal itself, right? The signal itself goes out. This CT from here, it goes out. It passes through this phi gate. We're going to talk about phi very soon. And it goes into that phi gate, and this becomes the output eventually. That's a new HT. So this becomes a new HT you will see here, right? So this is kind of how it is, right? This is kind of a skeleton of it. And I'm going to do breakdown next slide. But I just wanted, in case you did not observe it, I wanted everyone to kind of observe that, see that pattern. There's a pattern there, right? The pattern is that you have cell state keeps moving, right? Then, but here you have the forget gate that modulates what comes in. Then you have the input modulation gate, right? And then that cell state, some part of it is taken out, something is done to it, right? And it becomes the output. So we're going to talk about those additional ones. Next slide. Okay. So the main thing is this, right? Each of these three gates, the forget gate, the input gate, the output gate, is learning something, right? And what it's learning is what should it keep from previous memory and what should it discard. Okay. So we're going to look at them. So let's start with the first one. You now see that here, it is now drawn the way I drew, except that this line here at the top is the cell state. So it's not labeled here, but let me label it properly. So this is the cell state, which is C, right? This is the cell state, C. And it is the same cell state that goes out. Okay, so you could call this CT minus one, while the one that's going out is CT plus one. Sorry, CT. Okay, now the first gate that affects the CT is the forget. The forget gate is obtained by taking the input, right? And then taking a measure of the previous output, right? The previous cell state, right? And then adding them together, okay? Then you apply a weight to them. You apply a weight to them, and then you apply the sigmoid gate. So that's this FT here. FT is the forget gate, what comes. And you normally take this FT and multiply it by CT, right? This is a product. But forget gate is, what this means basically is the weight, this weight. Remember, anytime you see W, that's the weight, that's a parameter, that's what is learning. That's the part of the neural network that is changing values, the back propagation and the parameter, that's what is changing value. That's what it's learning. Is a weight that determines how much of each signal goes in to the next layer and so on. So this HT minus 1 XT is combined. Basically, it's a combination of the previous hidden state and the current input. Sometimes this combination can be a concatenation, and I think that's usually what happens. Basically, they join them together. They don't sum. It's not a sum, right? Unlike the other one, but in LSTM, it's not a sum, as you can see here. It's an extension. So they are concatenated. They are multiplied by the weight. That gives you a new, output, right? That output is then passed through a sigmoid function. So the sigmoid function is the gate that determines how much of these signals go through. But of course, the weight that you apply is what transforms this so that the sigmoid function can have impact of filtering out the things that matter. So what the forget gate actually does is essentially determining how much of the previous state should be forgotten and left behind. In other words, how much of previous events or previous memories or previous history should be forgotten. That's why it's called a forget gate and left behind. So that gives you FT. Basically, it decides what to erase. Then the next gate is the input gate. The input gate is IT, right? IT is also similar to the forget gate, exactly the same mathematical function, basically same implementation from span of neural network. It is still a concatenation of the previous hidden state and the current input, right? But now you have a different set of weights. So you now see where the increased what they usually call the basically it has more room to learn more things, basically more parameters, I will put it that way, right? That ability to learn more stuff comes from the fact that you have another set of weights, another set of parameters here, where it learns how much of the input should come in. So the interesting thing is that in both cases, we are still using both hidden and input. You could have said, okay, this forget gate since we are trying to learn how much we should forget, why are we bringing in the XT, which is the current input? We should only bring in the HT, which is the previous state, because that's what determines, how much we want to forget. But no, because we may have a situation where this how much you forget or how much you want to forget depends on the actual number of inputs or the actual specific inputs. The inputs that come in may be contribution or the features in there may contribute to determining how much should be forgotten. So that's why the input is added. Similarly, here you would have said, okay, for the input gate, why am I putting the past history, which is the hidden state, the previous hidden state, into the input gate, right? Because I only want to gate the input. But again, just like we argued here, the previous state may also have features that have a say in what should be allowed in from the current. So that's why at the end of the day, both sets of um, inputs are used along with the weights, right? So, but the interesting thing is that the LSTM is going to learn two different things entirely. LSTM is going to learn two different things, right? LSTM is not going to end up learning, maybe um, it's not going to learn the weights ensure that it learns what you want it to learn. I guess that's the point I'm trying to. The weights ensure that it learns what you want. So, right. So now we have talked about the two gates. They are basically the same. They are both derived from the same thing. The input gate is derived from previous. I'm sorry, the forget gate is derived from previous input, previous hidden state, current input, or a different set of weights. Still the same sigmoid gating function. Then the input gates, again, previous experiences, previous historical state, and current input, or different set of weights, the gating function. Okay. So when these two now come together, you now have the CT, right? The new cell state is obtained by multiplying the forget gate. Basically, how much do you want to forget? You multiply it by the previous cell state. Because the cell state is really the measure of the how much the cell state, that's the cell state, that's what keeps that historical state, what you are remembering, what you're forgetting. So you apply FT, which is a forget gate, to the previous history, right? And then you add IT, okay? IT, which is the input gate to this CT hat. The CT hat is the new cell state, the new derived state, what it should look like, right? And we're going to look at what this new derived state. So in this sense, the final cell state comes from a combination of a certain proportion of the previous cell state, right? What was already there, the previous knowledge, plus a certain proportion also determined by the input gate of the new information. This new information is now obtained from the XT, which is what we'll see there. And if you look at that in the next, the new cell states, right, which we call the candidate memory, is basically again obtained from still taking the same inputs, right? Same two um, previous um, states, previous hidden states, right, or previous output. Because for a for you get the output the same way basically, right? But previous hidden state and you multiply by another set of weights, which is what for the candidate memory. This is what we actually want to learn, the new things we want, and we pass it through a band gate. Sorry, it's not a gate, it's a band activation function. So you see that here, this is the only one that is not a gate. It's an activation function. So that section that I told you that is supposed to be very sharp because you don't want that band to be large, right? For a TAN, it's going to be much wider. So this is going to be standard normal TAN activation function, and that's this CT. So is this CT now that will be multiplied by this IT. So the IT is the input gate that determines how much of the input should come, and then it'll be added to the CT minus one, the previous cell state, but not all of the previous cell state, a certain fraction of it as determined by this forget gate. Okay, that gives us a new cell state. That's it, right? So that is again what this building depicts, which I think the symbols are hidden so we can see. So you will see that this is the previous cell state. This is the new cell state. Now, the first thing that happens is that we will take the forget gate. The forget gate is HT minus 1 and XT combined. These are around, they are not summed together, but they are kind of flattened and placed together side by side. And that this forms the input that all four of them will use. So the first one is forget gate. You gate on it with its own weight. Remember, there's a weight here, that's a WF, right? Before it goes into the gating function. Well, typically, when we see the gating function, we assume that weights are applied to it. So a certain amount of this, remember, this is always going to be zeros or ones. Very numbers are very close to zero or very close to, right? So that will determine how much of this, right? Because it's multiplication, it's also going to gate CT minus one. So it's basically going to determine which of the features from the previous history pass through. That's the first, that's the forget gate. Then you now have the input gate, but the input gate is going to act on the input itself. And the input is still the same input, but you now have the weight, its own weight and activation function that comes in. So the input gate now gets how much of the input also comes through. So which of these features from the input matters most? That's what comes out here. And then those two are added. The features that matters most from the current input, plus the features that matter most from the previous historical cell state, right? Those are now used to make up the new cell state. Then the output, which is what you use to compare and train the model, is obtained by taking this new cell state and pass it through a TAN function. And then you now use the output gate, which is the third gate, right? The output gate still takes the same input, right? It has its own output weight and it is gated. So it gives you the output gate value, right? That output gate value is now what is used to determine how much of the cell state is used as output. And so whenever you have gating, you see it's a multiplier, it's multiplication. So it always kind of masks out some things and leaves some things. Yeah, that's what those do. So this is kind of an internal analysis. You can see all the maths, right? But I think you should look beyond the maths at the equation of how did they even come up with this kind of idea? The idea was simply the mathematical implementation. Forget the maths. It is more about what's the idea behind this. The idea behind this is take the previous state of the cell, previous hidden state, that's HT minus, right? And then take the current input. That forms the new meta input. Then from this new meta input, you will use it to gate how much of the previous cell state gets carried over, and how much of the current new state, which comes from the new input, gets carried over and summed. That forms a new cell state. So what we are saying essentially is that the LSTM is a layer that is able to learn to forget some things that are not necessary from historical parts of the sequence, while keeping some things that it has learned that are necessary from the current part of the sequence. And that is what it uses to generate the output. As simple as that. The rest of it is the maths that's used to achieve that. So the question is how come that this whole thing now solves vanishing gradients? Because we have effectively changed a multiplication problem into an addition problem. If you look at it, the new cell state is how much of the old cell state we want to take plus how much of the current state we want to take. It is now a sum. So if you do the gradient calculation from this, right, you'll find that it is no more a product of gradients. Sorry, it's no more a product of weights. It is now a sum of weights because the forget you know gate is basically dominated by that weight, the WT, right? The WF rather. The inputs gate is dominated by that weight WI, which we would have seen here, the WF and the WI, right? If you do some kind of factorization or something, okay. So it is no more a product of weights. It's now some weights. So instead of multiplying repeatedly, right, the cell state now becomes a continuity of previous state, but added on to new state. So it uses addition, right? So if you were to do the derivative of addition, it's always going to be one. But if you were to do derivative of multiplication, it approaches zero, like we just saw where you multiply small numbers over time. But if you multiply small numbers, so if you add small numbers, it actually approaches one. Yes, it can go above one, but it is not rising exponentially or falling exponentially, just remains kind of stable. That is how you were able to fix um, um, the uh, the vanishing gradient or exploding gradient. So the result we get is that we have more stable gradient field. We have long-term memory. That's why it's called the long short-term memory. It actually is a combination of a long-term memory, which is what the forget gate determines, and the short-term memory, which is what the input gate determines, right? So it is able to remember long sequences and even remember the influence of more recent events, right, in the long sequence and how it connects to much older events in the long sequence. So it is much better for language modeling because in language, I can speak a long sentence, right, that is very long, but the last word I say is actually still connected to the very first one I said, like a minute or so ago in that long speech. So you needed LSTM to be able to really uh, represent or label language. So before the advent of transformers, which is what we'll talk about next, LSTMs were like the key neural network architecture that powered anything that has to do with natural language processing, right? Including things like the Google Voice, machine translation, speech recognition, text recognition, so on. So for you to do LSTM with PyTorch is quite simple. You just use the LSTM function. Just like we talked about, you specify the input size. So this input size is the number of features coming into the input, not the sequence length, right? The hidden size is the number of features coming out from the LSTM, right? And then batch first truth. So this is more or less the same drop-in replacement for a recurrent neural network. And then as just as everything else, you still need to do that final linear layer, right? That will do the knowledge representation. Okay, so the last architecture we're going to talk about when it comes to sequence models is the GRU, the gated current unit. So, why did people not rest after LSTM solved all the problems? They still decided, okay, let's still improve some more. Then they came up with this GRU. The main reason was that LSTMs were very good for solving those long sequence problems. But the main problem what they have with them is slow. We're actually going to see it when we use an LSTM versus a GRE to train on a sequence of um, words or sentences. The LSTM text is computationally heavy. And it's obvious for you to see because if you just go and look at how much computation is going on here, this is a lot. Each of these WF this that you are seeing here, this is a matrix multiplication, a matrix dot product, right? Each of these. So you're doing matrix dot products, and these are long sequences. Okay. Then the back propagation, you're also going to do the same um, gradient reverse of these matrix dot products over long sequences. So by the time you finish all of this for training a model, it took a lot of time. It was computationally heavy, right? There were a lot of parameters as well. You know, training was slow. So researchers were asking themselves, how can we improve this? How can we simplify this? That's how the GRU came up. So GRU came about as a result of experiences that people had with LSTM compared to RNN. So they eventually were able to learn which aspect of the LSTM really mattered to that vanishing gradient problem. And they were able to fine tune it, drop some parts of the architecture that were not really contributing to that. And they came up with the GRU. The GRU is now a more simplified version of the LSTM. It has just two gates. It doesn't have, it just has an update gate and a reset gate. And it doesn't have a separate cell state. So they went back to having just a single cell state. Remember that with LSTM, a second cell state was introduced. So you have the HT, which is the hidden state, right? That you use to essentially, that's basically the output, right? The output becomes a hidden state. Right? Uh, and then they still maintain a cell state. And they say hidden state, which is the output I use again, to create the new concatenated inputs that you use to generate the forget input and output kits. But with GRU, they said, well, do we really need another cell state? They took that one out first, right? And then the second question, do we really need three gates? They took one out. So we ended up with just two gates, the update gate, the reset gate, and just one cell state. So here, this is how it is kind of represented. We're going to look at the maths again. But you now have the previous hidden state. It's still kind of concatenated with the current input, right? To form this input. We only need to calculate two gates. So we have the update gate, which is the RT. The update gate now determines how much of the previous, how much of the previous um, hidden state comes across, right? And then it's concatenated again with the input, then goes straight to the tab. Then you have a reset gate. And the reset gate, we'll look at it in detail before we see the math show. So the result of the GRU is that GRU was far less parameters, so it was faster to train. You don't the other one, LSTM, you have two tanks, but this one you have just one tank. You have three sigmoids, but here you have just one sigmoid. Even the activation functions are pretty fast, but I think sigmoid and tan are some of the slowest activation functions that we have because of the exponential calculation that needs to be done. So it actually helped to drop one tan and drop one sigmoid, in addition to you know all of the other calculations and the weights. So right now in industry, GRU is preferred uh, for uh, sequence models. So how the GRU works is that instead of blindly updating memory, right, the network can control memory flow with bits. So GRU will maintain a single state, that's the HT, the hidden state, right? And then the hidden state is then combined with the input states, just like it was done for LSTMs. Okay. When you combine the hidden state with the input state, then you will have the update weights and the update gates. So the update gate is a ZT, which tells how much of the past should be brought in. So that's similar to the forget gate in LSTM. That's this, right? How much of the past you want to bring into new hidden state. So this is a simple equation for that. Then you have a reset gate. Reset gate is like the forget gate, right? How much of the past should we forget? Well, I think you could also look at it as update gate is effectively had to just do with the past, right? How much of the past should we keep and how much of the past should we forget, right? So um the reset gate basically is going to reset some aspects of the previous state. So, but it's still the same thing. You have weight here. The weight will determine how much of these features come, how much of the features are in this reset gate RT, right? So you just have ZT and RT. And that's what you're seeing here. So the inputs and the hidden state are combined together to form the meta input that is used through the update gate and the reset gate, right? And then what now happens is those two are then combined, right? And used to calculate the new output. Simple. And the new hidden state and the new output, right? So if values are close to 1, that means keep the old memory. That's for update gate. If values are close to 0 for those specific features. Basically, suppressing some features allows others to come through. And the same thing for reset gate. If the values are close to 1, that means forget it, right? Or reset it. Values are close to 0, allow more of the memory to come, right? So at the end of the day, you keep the hidden state, and that is basically the memory at each time step. So it's just a slightly slicker version of the LSTM. And that's it, right? If we want to look at it from here, so you have the candidate memory, which is the new information. The candidate memory, now you have the W, which is the actual weight of the GRU. Okay. So you notice that, yeah, we still have weights for the update gate and we have weights for the reset gate, but we also have one with set of weights. So if you remember, LSTM had 5 sets of weights, but GRU has 3 because the output gate was dropped and cell state was also dropped. So with that, you now have this, right, which is still there's a slight difference here. The new candidate memory is how much of the previous memory wants to reset. This is basically the reset gate. How much of it do you want to reset? You use that reset gate and you multiply by previous memory, and then you flatten it, concatenate it with the input, okay, multiply by the weight, you get the new hidden state. So it's a much simpler, um, direct, calculation for the hidden states. So the reset gate decides how much past contributes. The final memory is now obtained, the final state, the final hidden state will be 1 minus the update, right? 1 minus the update weight times the previous state plus the update weight times this this candidate memory. So here you now see this is still addition, just like the LSTM, and it's not repeated multiplication. So GRU matters because GRU introduced a new idea that instead of trying to overwrite memory, you control it, right? And that is what is done here. First of all, with this reset gate. So the reset gate is effectively controlling how much of the memory is gating how much of the memory gets comes in, right? And then um, the update gate determines the proportion. It's kind of push-pull. That's why we're having 1 minus Z on one side and Z on the other side. If Z is higher, right, that means more of less of the history comes in and more of the current um, information, new information stays. But if Z is lower, that means more of the history comes in and less of this comes. So this, no, that's the maths of it. And this is just representing the maths of it, right? Where you have the XT, this is the previous HT. HT comes in, right? The HT and the XT are combined, right? And then you have this gating. And this gating is actually used to gate. This is the reset gate. It's used to gate how much of the previous memory comes in, right, into the actual new memory that we are creating. Okay. And um, the input X is also used to generate this. So the 1 minus gives us this behavior here, where we are saying we're combining these two, right? But we are flipping it. That is what gives us this. So that's a summary of GRU. You have update gates again. You have reset gate, right? Update gate and reset gate are obtained the same way. The only difference is that the weights are different. But the candidate memory, which is the main thing, you gate how much of the previous history comes using the reset gate. Get how much of it comes. And then that gives you the candidate memory. And then the final update will be basically based on the update gate. More of basically it's a complementary sum. 0.5, if it is 0.5, then 0.5, 0.5, or 0.6, 0.4. It's kind of a percentage thing. It's a zero something basically. That's what this is saying. That the final update if you take 60% of current memory, you have to take 40% of previous memory, right? If you take 10% of current memory, then you take 90% of previous. So it learns basically that. But the most important thing at the end of the day is that it is additive, right? So the additiveness is what allows the vanishing gradients to go away. So the gated memory GRU you can think of it as and the middle ground between the recurrent neural network and LSTM. Recurrent neural network was the simplest form, fastest to train and everything, but it had vanishing gradient problems. LSTM solved that problem, but at much higher complexity. So GRU was kind of middle ground, based on the learnings from both sides, from both experiences to come up with a um, a model or an architecture, a layer that essentially brings in the best of both worlds. Right. So that's it. If you are training your model, typically, I think you just start with a GRU, right? Especially if your data set is smaller, if latency matters, if training budget is limited. But one thing is, though GRU are simplified, but it is still not as good as LSTM on very, very long sequences. So there are still places where LSTM is still much better, but you can use GRU for most sequence problems that you have. That's the most important thing, right? That you have to remember. GRU has fewer parameters. GRU is faster to train. Long sequences is very good, but LSTM is still the best.
in all of them. Of course, it has more parameters. The only downside is just that it is slower. Right? So again, this is how you do GRU. Again, it's still the same thing. Specify the input size, specify the hidden size, and so most of the time, if you are switching from LSTM to GRU, it's just one line of code. So remember what we said. This is not really about the code. Machine learning is not really about the code. It's about understanding of the concepts. So that when you are deciding on architecture, somebody asks you, okay, what's the best architecture for this kind of problem? Then should I use LSTM or should I use GRE? And if I'm to use LSTM, why? Why is it better? Or if I'm to use GRU, why? Why is it better if I'm to use RNN? Or should I use a transformer? Should I use a CNN? Right? These are the things that you need to understand. Because PyTorch makes things very easy. Now we even have JAX and so on. So being able to train models is not really about the code. It's more about understanding the problem, understanding the tooling that you have available, understanding the methods you have available, understanding the architectures that people have explored, and being able to make a good choice. That is what matters. So let's talk a little bit about sequence-to-sequence models. So a sequence-to-sequence model is a model where you are no more in all these ones, like when we do LSTMs. I think I'll just do a bit of hands-on later on. But because of the time constraint, I will just go through all the theory and then I can spend maybe 15, 20 minutes on the theory. But one thing is this, all this while we have been talking about LSTM, GRU, uh, we have been doing classification problem, even with CNNs, we have been doing classification problems. Classification problem is where you give your neural network input data and you ask it to classify based on that input data where it belongs, right? So for example, I give you a picture of a dog and you classify, okay, it's a dog or cat, or a picture of MNIST, for example, picture of images of handwritten characters, and you classify them whether it is 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? Cipher, you classify whether they are dogs or airplanes or cats or things like that. In sequence kind of problems, I can give you text and I tell you train this model so that it will classify this English, this prose or this text, whether it is positive sentiment or negative sentiment, right? Those are classification problems. So you get a sequence, right, coming in, but the output is a single classification or one out of, um, a number of categories. That is what we have been traditionally doing, right? Now, when we talk about sequence to sequence models, this is now another extra level of complexity. Sequence to sequence models are basically models where you are essentially training your model not to classify, but to generate a new sequence, basically. So the problem at hand that we're trying to solve is that you have an input and the input lengths are different from the output lengths. So a good example of sequence-to-sequence model is translation. The input is a sequence of words in one language. The output is another sequence of words in a different language. That's translation. Speech recognition. The input is a sequence of words from, sound bites, basically, waveform, right? But the output is a sequence of words in text, in, ASCII text that we can read. Summarization is a sequence of words from a larger, body of text. And the output is a sequence of words that represent a summary of that. That's a sequence problem. So the main challenge with sequence problem is that the lengths are different. So how do we solve sequence to sequence problems, right? we use what we call an encoder-decoder architecture. We'll talk a bit more about this. Maybe I'll let us talk about it next week because we'll also use it and tee ourselves off into um, the concept of attention and transformers. Attention, we need to understand the concept of attention before we go into talking about the idea of transformers. So we'll talk about that next week, even though I want to still introduce it a little bit, right? So the encoder-decoder architecture, we first of all need to understand what an encoder is. An encoder is something that will compress a long sequence into a single internal meaning or representation, the hidden meaning. That hidden meaning, when we're talking about hidden state, right? That is a representation of what the neural network, the model has learned about that sequence. Is represented by the hidden state, right? That hidden state is sometimes called a context vector because that context vector is a single vector, right? That represents an entire sequence that came in. So an encoder, what we've been doing all this while, basically have been encoders, right? The encoder takes a sequence and generates a single context vector that represents the meaning of that sequence based on the data you trained it on. That is what an encoder is. But a decoder does the opposite. A decoder will take this same context vector as its own input and then generate a new sequence. And that's how we're able to solve these sequence-to-sequence problems. Because what it means then is that I can take an encoder that I have trained to, understand English, right? So any sentence that I give it in English, it is going to take that sentence and it's going to give me a context vector that represents the meaning of that sentence. Then I can train a decoder to take the same context vector and generate another sequence that represents that same meaning in French. And with that, you have generated language translator. And that's how these things work, basically. Language translator, all of those things, we got them by basically combining an encoder that learns in one language with a decoder that learns, that is able to generate output in another language. That is what that's what a sequence model, does, right? That's what sequence to sequence models do. Okay, now, if you were to take the decoder and instead of training it to generate the sequence that has that same meaning, you rather generate maybe a summary of what was said, a shorter version. Then you have essentially created a summarization model. Okay, so you can now see that it is an all-purpose thing, right? It is an all-purpose thing. That idea can be reused to solve so many different classes of problems, right? So typically that means you have a pipeline where you have an input, you have an encoder, the encoder generates a context vector, right? That same context vector, you pass it into a decoder that you have trained. The decoder will now generate an output that basically pulls out another sequence that has the same meaning, as a context vector, but maybe in another domain, either in another language or as a summary or something, right? And this is a design that powered all the early translation systems that we had. Okay, so that's what sequence model is. Then we have what we call teacher forcing. We're going to go into all of this later on, but we'll take a whole day to talk about sequence models, and we'll talk about attention mechanism. Teacher forcing is a method where you are showing the decoder every single token that it must predict, one token at a time, right? Okay. So instead of feeding the model with the prediction, you feed it with the correct token during training. Okay, but we'll talk about all of this, right? And this is how sequence to sequence looks like. So when we've talked about sequence to sequence models, which we'll go into detail, the next thing would be, okay, what next? Then we'll look at that. We'll look at how all of this works. And then we'll talk about context vector bottleneck, and then the attention mechanism that solved that context vector bottleneck. And then attention was a breakthrough that led to um, the transformers of today. Transformers are now the progenitors of the large language models that we use today. So we will study that architecture, and we will we'll actually do some of it, you know. Okay, so let's do a bit of hands-on. Let's just do a little bit of hands-on just to see what we can do with a long short-term memory. But it's not really hard, right? It's not hard. Okay, yeah, just give me a second. Uh, okay, so let's look at some examples of I want to bring up simple, maybe because of the time, but we can just do an example with a new collab notebook. All right, so we're just going to look at how you can model a sequence. We just look at how you can do, what we have done with GRU. Um, Let me bring it up. I think we can, how we move from a feed-forward network, right, to GRU, sorry, to RNN, to LSTM, and to GRU. So when we look at that, you are going to also be able to see how those are implemented. Okay, so we start off with this, right? And I think I had already explained this, right? This is a single representation, right? You have the layer here, and then you have the loop back output back into input. Okay. And then this is the unrolled form. So that just keeps us, takes us back. So this is the original data. Now we have basically simplified this to very simple data structures or tensors that will be easy for us to visualize. But in real cases, right, we are dealing with very large dimensional numbers, right? This is a sequence, 5 numbers, okay? But in reality, each of these 5 numbers represent this sequence. Each of them is a feature vector itself. So it would have a second dimension. But right now we're just going with a single dimension feature vector, but we'll touch as we move on. So now, if we want to, this is the original data, the original sequence, we want to now train a model to be able to predict this. This is a very simple sequence, so it's not even a big problem for any, even a simple, fully connected network can learn this, right? So, yeah, so you first of all create your X and your Y data. Remember, when you're predicting a sequence it's easy to get data for training models, based on sequence data. Because sequence data is something like if there is nothing, then start with 1. If there is 1, then predict 2. If there's 1, 2, then predict 3. If there's 1, 2, 3, then predict 4. If there's 1, 2, 3, 4, then predict 5. That's basically what these are doing. So what this is saying is that the first data set, the first data point or sample is going to be generated by if the only number in the list is 1, then y, which is the um, true values, what the model should be predicting, what you are training it to predict, y should be 2. Then if x is 1, 2, that means the sequence is 1, 2, then y should be the next number in that model, in that sequence, and that's 3, right? And it just goes that way, 1, 2, 3, then it should predict 4. 1, 2, 3, 4, then it should predict 5. That's it. So you start with that, right? That's how you generate training data from a sequence. And this will be the pattern that we'll be using a lot. Now, um, um, I don't know why this is saying not enough values to unpack. Expected to got 0. Um, so this should actually be written this way: x comma y equals 0, equals 2RA. So that triple is what we are trying to predict, right? Even though I wasn't writing this, um, I guess it was trying to understand that one as a different thing. But yeah, well, okay. So all right. So we have, if we now go check X and Y now, which is really what this is about, you will see that for each X, the Y is the next number that follows that sequence of X's. So for this X that is 1, the Y is 2. For this X that is 1, 2, the Y is 3. For this X that is 1, 2, 3, right, the Y is 4.
For this x is 1, 2, 3, 4, the y is 5. So this is basically um, sequence, right? Now, so that's the first thing. Then the second thing is, yeah, we just go ahead. If you don't have PyTorch, then you can, have all of Torch, Matplotlib, NumPy, but these are already there. So we import them. So what we want to achieve with this experiment is train a model to predict the next value of a noisy sine wave, right? Um, Even though, to be honest, a noisy sine wave is not good enough to differentiate, because a noisy sine wave has mathematical correlation between the points. So even a fully connected neural network can predict it. It's not really sequential in that manner. But this is just a demo to allow us see how it works. It requires memory, right? It is visually intuitive, and it exposes weaknesses of RNN. Again, this didn't really expose the RNN weaknesses because of the fact that it is sine wave and the sequence wasn't long enough. So when we do this again, I'm going to swap this out and bring in data that is more challenging for RNN. So anyway, this is um, sine wave data. So basically it just uses a sine equation. I'm going to get better data, from Kaggle for this. I'll be looking for that to see if we can get better data. Anyway, so this just generates that data, right? And yeah, so this just generates a sine wave. I'll swap this out with another kind of data set, but let's just run this. So this is how you visualize. So basically, you're just taking each of the values of x and you plot, a single dot corresponding to the x and y values there. So that will give you this. You can see it's kind of a funny sine wave. All right. So we now try to use different models to predict the next in this data, right? Um, so we have, um, yeah, we try to train a feed forward. So feed forward is a simple feed forward. You use NN sequential. We have linear ReLU, and we have another linear. So you have linear ReLU and then linear, right? So because we are trying to do regression, it's a regression problem. We're not trying to do classification. So we don't need any other activation function, right? So forward is just to pass it through, right? Then X, we take the X value and we have 1,000 X values and 50. So 50 is the sequence length. So remember, we're dealing with sequences here. So we first of all get the sequence. If you actually look at it, remember we have to generate the sequences. And this one was just the shape of X, right? But if we print out X itself, you see that X is made up of sequence of numbers, right? So it's a sequence of numbers, but we have to squeeze it we have to squeeze the last dimension. Squeeze in PyTorch, what it does is it removes a dimension that doesn't have more than one element in it, right? And turns it into a single dimension. So perhaps this is X, but X dot squeeze minus 1 will look a bit different. So you now see x dot squeeze now becomes two-dimensional instead of 3 dimensions. X alone has 3 dimensions. Just pay attention and look at it. Let me do that again. You can see that 3 brackets at the beginning. That's how you know the number of dimensions, right? But we turn it into two-dimensional because it should actually be three-dimensional if the third dimension had multiple features, right? But here we're just picking only one feature, which is the number on the chart. But the number is a sequence. So like this one, this is a sequence of the numbers that make up that that single sinusoid. And this is again another number, another sequence, right? Another sequence, so on. Remember, the sequences are generated by looking at um, from one point in the sine wave to the next point, right? So for example, from this point in the sine wave to the corresponding this point, right? All of this, we take all of these points, that forms the sequence. Another one can start from here, right? And like that. Okay. So so that's uh that's that. Okay. Now, um for for a simple um fully connected network, right? Order doesn't matter, right? Mm. So we now train uh the this model, but of course we have to do a reusable training function first. So we use Adam, we use mean square error loss because it's a regression problem. We're trying to predict specific values rather than classification or categories. And we do the normal thing, prediction, calculate the loss function, do the zero grad, do the backward prop, back prop, do the optimizer step to update the parameters, and we track the loss. So that's the whole function. Then this is the evaluation part of the function where we just calculate accuracy. Accuracy is basically how far away prediction is from the actual value using the mean square error. This is the mean. Okay, this is the mean absolute error actually. This is the mean absolute error. You're taking mean of the absolute value of the differences. Um, so it's interesting that I did mean, yeah, okay, that's correct. Mean in one direction. Um, mean divided by y. I need to check that. Okay. So we now train the simple model, right? The feed-forward model, which we train it and a few epochs, 50 epochs, right? And we're able to get it from 0.5 error to 0.01, basically. And then we can plot the loss. And that's it. Now, this is loss. Now let's do recurrent neural network. So you can see recurrent neural network is actually very easy. You just use nn.rnn. Specify the input size. There will be only one input size because there's only one input feature, the single number that we are predicting. Okay. The hidden size can be anything, right? Hidden size normally is higher because hidden size represents the internal meaning of the sequences, right? So you cannot use the same one neuron. That will not work, or one feature. So we use 32 and batch first is true. And then we still do a linear um, layer. So whenever you're using sequence models, after the sequence layer itself, whatever the layer is, you always still need a fully connected layer to then bring it to the output you want. In this case, the output we want is one. Again, we want to predict just one value. So you typically want to do flatten or something, right?
And we're going to look at more detail or in more detail at I think I had kind of shown you how the shape of the input is and the shape of the output is and all of that. So yeah. So this is using a simple recurrent neural network, right? A single layer of an RNN, right? And then the fully connected layer. So you train this and it drops to 0.0185. It's basically almost the same thing as this. In fact, it even looks like the loss is a bit higher. So we can compare the losses, right? RNN even took a bit longer. So, but again, this is because we are using mathematical data, all right? Um, if we are trying to, let me look for real challenging data, not this kind of artificial. So let's say we want to do forecasting, for example, financial markets. Yeah, let's do that because I think that is information that is easier for recurrent neural networks to predict. Because using a simple, it will not really give us what we want. So let's see. So there's a data set on cargo that we will use crypto forecasting. Okay, we're going to use this. So this crypto forecasting is a data set that allows um, basically it's a research cryptocurrencies, cryptocurrencies fluctuate a lot, right? And sometimes you don't know what is driving the fluctuations. Um, so uh, what we typically try to do is I know a lot of people who are using bots, right, to try to do that prediction. So it may not necessarily work out, but I think the bots are pretty good at it. So now um, it's very volatile, right? Um, the correlation, you may not really see correlation, but there are things happening in the background, right, that kind of affect all these things. So maybe you may be able to see correlation. So what we are going to do is we will take a sample of this data and take a time-bound sample. So I'm just going to go into the data. If you look at this, right, the training set, it has a timestamp. It has asset ID, number of trades, open, high, low. So these are the different um, features, right, that you would bring into this for each data set. Okay. Um, so what you could do is take this. We have examples here. So asset details, sample submission, supplementary. Okay. There are some files in here. Um, so we can go with the train.csv. Oh, we have to log in. So I cannot use this. Let's see. Let's see if I can log into Cargo. It's been a while.
Okay, so that's going to take a bit of time to access that information. So I will look for another one. Um, One really good data set that I think we can use, but I didn't want to bring that one up at this stage, is there is this predictive maintenance data set that you can use to predict when an equipment will fail, right? What they call remaining user life. Okay, so let's see if I can get that one. So this was actually brought by NASA, and a lot of people have kind of done different things to it. So uh, the whole idea is, um, yeah. So let's see. I think I can just get it um, directly. Um, let's see. It's aircraft engine. So let's get that one. Just I'm going to get just the first few lines and predict. Even though this might be more difficult, which is okay. It's just for us to demo the differences. Maybe we'll pick one parameter and ask it to predict. But typically what we predict is the remaining useful life. Okay. So this is um it's a predictive. It's predictive aircraft maintenance. So the idea is this. Um, this data is used for training aircraft to look at different inputs that come from different sensors, right? And then those different inputs from different sensors will be used to kind of predict when that equipment will fail or when that aircraft will fail. So we have PM test, PM train, PM truth. Okay. Those are three files in here. So let's go with this one. There are different variations of it, which we can use. I think this will be a much better, it's going to be a much better, um, let me make a copy. It's going to be much better example to differentiate those three than if we just used, this simplified, um, you know, sine wave thing. So let's do that. So let's say, get predictive um, maintenance data. Can and it's just let's have a fixed sequence length. Um, yeah, let's have a fixed sequence length. Yeah, sequence length just for the purpose of what we did here. Here we had a sequence length of 50. So in order not to go beyond that, let's have a sequence length of 50. So we will first import cargo hub as KH. And then we will now KH dot data set download. And then I will pass in this. And that should be the path. Okay. Then from what we have seen here, we'll just we'll load the truth. Truth is the value that represents um, the um, the number of days left remaining useful life. So, but I'm not going to do that. Rather, I'm going to use the train value and I will see if I can predict um, something in this sequence, which there are 26 columns here. Yeah, let me select all. So I want to see if I can predict something else, the next value in the sequence, right? But a lot of these values, in a lot of these values, most of them are similar. Not much is changing, right? But there are some also where it is changing. So for example, this one, you can see the distribution is high, but this one, all of them are basically the same value. All of them here are basically the same value. So we don't know what this actually mean, right? But I'll just pick one of them to be, or to predict the next in the sequence, right? You want to predict the next, because sequence data is being able to predict what the next value is, and the next value can actually be an entire, you know, vector. So it's a bit more complex than what I wanted. I wanted a sequence that is maybe a um, single feature, or maybe two or three features. Let's see if we can find something like that. Um, so let's see, we can just search for it. Um, sequence cargo data for training RNN with only one or two, let me say two or three features and short sequence length. Okay, so we have daily minimum temperatures um, in Melbourne. We have international airline passengers. There's custom synthetic sine cosine data, what I was running away from. So, but let's see if this, let's see if this will work. Any of them we can use. Okay, so this is sequence data with the date time series and the daily minimum temperature. So we can use this um, date and daily minimum. We can basically just use only the temperature because it's sequence, and see if it can predict. So let's use this just for purpose of demo. So I'm going to take this and we'll give we'll give attribution to all of those that we are using their data. Okay, so this is that one. To get the path, then if you look at that data, there is just a single file called daily minimum temperatures in ME. So we can just use that. I don't need to go and start exploring to find out. But then we can also do that as well. So, okay. Um, so let's do something like OS. Um, let's just download it straight up. I may not have enough time to call the function again. All right. But let's start from the top again. All right. So remember in sequential data, there are two ways you can have a fixed window approach, or you could have a a um a mod a variable length sequence where you do padding. But I'm not going to do that one now because that one is a bit complicated, right? Um, okay. So okay. So this is not, for some reason, the handle is different. Um, so let's try this one. This one is airplane time series, which is the number of passengers in an airplane. So let's try this one. Okay. Okay, so maybe I'm doing, oh, okay, that was from me. The slash at the beginning was the problem. Okay, so that was my bad. Um, so the other one was still okay. We can still get it as well if we want to. But I think yeah, we can try both. I think we can try both. So let's get both as well. Um, so we have two sets of parts. Um, so we have airplane passengers, then we can just load this into a pandas data frame as we usually do. Import pandas as PD, then PD df equals PD dot read CSV path plus slash whatever we had here, airplane passengers dot CSV. and that's the data frame. So this should just be so it's just a month and then the passengers. So maybe there's a pattern, right? So let's call this airplane, while this one is for minimum daily temperature. So again, we will also take the path and we can do path, sorry, airplane, sorry, temperature data frame. Yeah, daily minimum temperatures in Melbourne. Okay, right. Okay, looks like this one is slightly different. Now I wonder why. Mm, it says error expected two fields in line 3653 and saw 3. That's interesting. Um, hmm. Okay, well, I think we just skip it. We can address it later. So let's go with the airline data, right? The airline sequential data. And just like, to generate the data, right, we would have to run through the sequence, right? And let's say we want a fixed sequence length of 50. You can see that there are 143 rows here. So we can take from the first input to 140 first to the 50th, then this 51st will be the Y value. That's how you generate the prediction, because you want to predict what the next um value should be. So that means the Y should always be the value at the end. So um if we have 50, a sequence length of 50, and we want a fixed length sequence length, while we have 143, right? The simple math that would tell you that the length is actually 51. So simple math would tell you that the number of times you would have to move, the number of windows or data sets you can get will be 143 minus 51, basically. 143 minus 51 plus 1. So let's go. So here we will generate the sequence. We'll generate the sequence. Generate sequence for the plane sequence. Sequence training data. Okay. So we will talk about. We can just say the window number of windows. I don't know what to call that. Um, Number of windows. Yeah, that's the number of windows. It's going to be the number of rows in the data frame airplane, right? Dot text. Or you can just say the length of the index, which is um, number of number of time steps, basically. So this length is 144, as you can see. but we're only going to take the second column because we don't know anything about the month. We're just trying to predict the sequence, right? So the month is not going to be part of the data. It's just going to be one-dimensional data. Um, as a matter of fact, we could do it this way. Let's do it this way. Let's start off by taking the X data sequence. Um, the entire sequence is going to be data frame um, passengers. That's really what it is. Dot value. Oh, this is airplane data frame. So it's just in some passenger. But we will take the with the shape as well. It's just one dimension. It's vectors. It's just one dimension. But we want to know the number of windows. So the number of windows minus how many we actually want. We want 50 um, per sequence. So we want to predict, given 50 at a time, we want to predict the next one, right? There are many different ways. This is a fixed window approach I want to use, but I want to get a lot of data. So we will. So here's the thing, right? I have a total of 144 numbers here, of which I'm going to take 50 numbers. So the first time I'll take 50, right? I don't know if this is 50, but let's just assume that first row is 50. Then the next time I'm going to start from this second one and take another 50. The next time start from the third one, take another 50. Right? That's how we want to generate this data. That's how you typically generate data for sequence training, right? You do that. Okay, and that's what we did for the sign, which has been done already. So we'll just do the same thing here. So for us to do that, we need to know how many windows we want to slide our starting point and start from. That's the formula for the windows. The formula for the windows is the length of the entire thing, which is the number of you know, basically it's now sequence of shape 0, which is the right? Um, it's no more length. It's just sequence of shape 0. That is the number of you know items in this entire series. But we are taking 50 at a time, so it will be minus 51 plus 1. It's always minus the number we are taking plus 1. So if the sequence length is just 1, that means it will be minus 1 plus 1, which is 0. So it will be back to the entire number here. So this is the number of windows we want to flip. So we can now do for I in the number of windows. So because the window size, so let's do a parameterization here. And let's even just turn into a function. And the function is generate sequence data. Okay. So this is sequence length, right? Which is what I was trying to do before. Right. So the number of windows is sequence of shape minus sequence length, right? Sequence length plus 1. So it should actually be sequence length plus 1 plus 1, right? Yeah. So the reason why is why is it plus 1 plus 1? The first plus 1 is because this sequence length is the number of X. Okay, yeah, I think that's okay. It's okay. It's just a sequence length plus 1. So, but we actually need to, we cannot start from, yeah, it has to be plus 1 because if we have to include Y in that sequence, otherwise we'll end up with, we'll get to the last point and there'll be no Y, so it should be plus 2. So let me put a comment there. This ensures we still have values. This includes y, basically. This includes y in the mix. Okay. So and then we can just start off with x, yeah, and y. Um, okay. All right. So I guess it has yeah, so number of windows is sequence or shape 0. We assume this sequence is a NumPy array. Um, so this by adding 2, it includes y in the mix. I hope that is understood. But if not, I think I tried to explain it because if there are 50x values, then y will make it 51, right? So the actual sequence length is not just its length of x, but the y. If you don't include that y, then you get to a point where you will shift your sequence to the end and there will be no y value for that last one. So you'll be in trouble. So the x append will be sequence I to I plus sequence length, not I plus 50, I plus sequence length minus 1. It's actually going to be minus 1 because you don't want to include the y there. While I plus sequence length. All right. So, and that will be it. Then you return the x and the y. That will be this generate sequence data. It's going to give you x and y, and this should match what we had before, where we were generating you know, it this way. Well, yeah. So this also did the touch tensor as well. So we will have a tensor that has you know, we have to unsqueeze and add an extra dimension. So let's do that as well so that it matches the same pattern. So we are going to return a touch dot tensor x dot unsqueeze minus 1, and then touch tensor y unsqueeze. So what this does is it allows us to now have that shape. So let's see how it looks like now. So we can say x and y is generate sequence data. Sequence we are passing it is a sequence, and the sequence length is 50, so we'll just leave it at that. And then we'll see how x looks like. X dot shape and y dot shape. Okay. All right, so we have a little challenge. Index 144 is out of bounds. Yeah, so I went all the way to number of windows. I should have gone to number of windows minus 1. Failed because of that. Okay. Index 144. Let's even see. Maybe I got something else wrong here. Let's print the number of windows. It's 96. So 50 plus 96, 51 plus 96. Oh yeah, so it should be minus 51 plus 96 is 147. So that's not correct. Um, if it was 144, if the sequence length was 1, we'll have to minus 1. Okay, yeah, so this should have been yeah, this I didn't think about this properly. It should have been minus sequence length minus 1. I'm sorry, minus sequence length plus 1, which is minus sequence length minus 1 plus 1, which is 0. That cancels it off. So that 2 was off by one mistake that I made. So if you want me to explain that, I can explain it a bit more, but I think we're out of time. So let's just run it. Yeah, my maths was a bit I forgot to do the all right, so this is a different problem. Um okay. Oh yes, so I forgot. So yeah, but I can do that. Sequence is an array. Okay. Yeah, it's a numpy array. Let me just do X and Y. All right, so oh yeah. Um I did not return. Yeah, that was we should return this tuple. I didn't return the tuple. Okay, so I think we are good now. Um so yeah, so we now have this. They're just 93 of them. Um each of them has a sequence length of 49. Um yeah. Oh yeah, so I should not do minus 1. That's I shouldn't do minus 1. That's why it gives me 49. All right, so we now have 9351. So there are 93 of them. Because of that calculation, we can extract length sequences of length 50. Only 93 of them can be extracted from this 144, right? Mainly because we need to keep one for the Y value, and that Y value has a value of 1. So that's our sequence, and we can now do a plot of it. Um, and you can see it's a different thing now. I just wanted to fit into what we had before. So we don't have 1,000 data sets, but we have 93 of them. Okay, so this is prediction of passenger. You can see it goes up and down, but not only does it go up and down, but it also tends to rise over time. Okay, so let's see if there is. This will be more difficult for a feed-forward network to predict. All right, so let's just keep going. So when we squeeze x to minus 1, we basically get the sequences. So basically we have 93 sequences of length 50. So each sequence has a fixed length of 50. In other words, that 50 months in that sequence that correspond to the passenger number of passengers for that month. Then the order matters, of course. We have a generic training function. We have a generic accuracy calculation function. So we now do feed forward. So here we had a very good loss here, but let's see what loss we get with this one. It's going to be higher loss because our feed forward network will not really be able to predict this because there really isn't a mathematical correlation here. Okay, so we have long and float. Yeah, so that's one thing I forgot. These are passenger. I should probably do some normalization here. Um, so let's normalize it with a fixed value. Remember, this is a sequence. We are going to have exploding gradients because of these high values. But if we divide everything by 1,000, right? I don't think we have a number that is more than 1,000. So we just divide by 1,000. So we have a fixed normalization factor. So yeah, so I'll do that as part of um, the original data preprocessing, right? So let's do that in the generate sequence data. Um, we will um, yeah, we could just do that here. We could just normalize both X and Y data. So X, okay. So because this is standard, well, we could just divide it by 1,000. But we would first of all have to add the type. So when you're doing touch tensor, you can specify the type. The type was float. Okay, and you divide by 1,000. So that's the normalization there. And let's put this on 2 lines so it's easy to understand. Then so we just normalize at the same time. So Y again, Y's are also in the same range. So we'll also make it float on squeeze, then divide by 1,000. Okay. So I can put a comment here to say something divide by 1,000 to normalize the values. Okay. So it's just a naive normalization, um, nothing, you know. All right. So now when we plot our visualization, this will be in the range of 0 to 1 now. It's actually really small, 0.4. So that's okay. So our training should be faster now, and we will not have that problem that we had of mismatching type, because we were training long versus um, I was trying to train, the data was not matching. Okay, so we have double and float. I already specified my own numbers as float. So I'm surprised that we're having double. I don't know where double came from. Maybe we should divide by 1,000 first before we because right now I'm not sure. Okay, this is float 64. So it actually became doubles when I divided by 1,000. Or maybe because I did not specify the float. Okay, it's because I specified Python's float. So um I should have used maybe torch or float, right? Torch.float is float 32, while Python's float is float 64. So again, this is something, let me just confirm. When I am plotting the X squeeze, um, yeah, so this is torch.float, so we will not have that problem. Type mismatch is a common problem. All right, so we trained it and we got from loss of 0.05 to 0.016, which is pretty interesting. All right. It's stochastic gradient descent, that's why it's jumping up and down. Now let's do RNN. So with the RNN, 0.0052. So RNN seems to have done a bit better than well, it's not even done better. So that's interesting. Maybe I need to train it a bit longer with yeah, so you can see that feed forward is even better than RNN. That's interesting. So for this is a new data set and we're having the same thing. It's possible that it's actually this passenger thing is also auto-generated. Now this is using this is much longer. Oh, okay, so here we are now using generate sign data much more much longer sequence length. Um yeah, I don't have that capability with our own data set. So I'll just let this one run. So with much longer sequence length, RNN, the the interesting thing is I still see that this the feed-forward network is still better than the recurrent neural network. So we've not found a problem where the order matters so much, right? And we're also running out of time. So let me just continue and finish running it. I'll share this code with you. Oh yeah, okay. So this is now where the RNN actually begins to perform better. Here we are using, this is back to our, sign data now with a much longer sequence length. So you could see that with the shorter sequence length of 50, feed forward was even better than RNN, mainly because the feed forward is less complex, so it learns faster. It has less parameters, so it learns faster, and its loss will be lower. But the RNN has more parameters. You need more time to actually train all the parameters to become as good. But when we increase the length of the sequence to 240, which unfortunately, I cannot do that with our um, airplane data because our airplane data is just 100, I think it's just 240 or so, or 140. So I cannot get a sequence length when that one, the maximum length is 140. But if you can see here with sinusoidal, you can already see that the RNN is now doing much better in predicting the sequence, right? Okay, so now here's LSTM. So LSTM, we can go for a much longer sequence. If you have enough time, you can try an even longer sequence, maybe like 500, 1000, right? Generate sine waves 1000 long, then you will see. But here you can also see that the LSTM is taking a bit longer to train. So this is one of the challenges with the LSTM. Then it takes much longer. but it converges faster. Even though this sequence, to be honest, this sequence length is not actually enough to differentiate between a recurrent neural network and an LSTM, right? It is not enough. The sequence lengths that really matters are very long sequences, maybe 200, 300, 1,000, like a whole book or a whole page of a book or 2 pages or 5 pages of a book, right? That is where you start seeing the difference between them. Okay, so let's just continue when this is done, then we'll see the plot of the recurrent neural network against the LSTM. And so interestingly, the RNN is still better than LSTM. Again, LSTM has more parameters, so um the loss will be a bit higher at the beginning. You have to train the parameters more, right? And at the end of it, they were more or less very tight because we are not yet in the range of sequence length that LSTM begins to show itself. So let's look at GRU, gated recurrent unit. So again, same, you see that the three of them basically is the same way that you use them. And then train the GRU is going to be a bit faster than LSTM. Not as fast as the RNN, but faster than LSTM. And it should be more accurate. But again, like we have seen, they are not, the sequence length is not long enough to be able to really, differentiate these three guys, right? So at this point, right, I am very slow. This training would have been much faster if I had used a GPU. Look at how long I have spent waiting. We have spent waiting for this, right? After this, I'm going to switch to GPU and show you how much faster this is. By the way, I need to check that I had done the necessary movements of each of these things into the GPU. I didn't do that here, um, but should probably be done after creating the data. Yeah, so let's get the device first. Uh, or maybe that's something. Let's see if I can do that really fast. Uh, let's see if I can do that fast. Um, yeah, let's see if I can do that fast. Device equals CPU. Okay, well, yeah, okay, so we can go with this. And for now, it's CPU. So feed forward to device. Uh, train. We'll have we have to also move this to device. We can move each of them to the device. To device. Okay. So that will make it faster. So same thing here. Oh yeah, one thing we should actually yeah, we can move the X and Y to device here. So X, Y equals X to device and Y to device. Okay. Mm. So with that, we don't need to have the device here. Okay. Um, yeah. The X long, we also need to move them to device as well. Oh, well, I could have just passed the device in as a, thing here and it will do that, but let's keep going. Okay. Um, so this is the LSTM model, as well. So RNN LSTM plot. Now the GRU model, to device. GRU is finished training now. So interestingly, um, they're all very close, as you can see. Mainly because they are not that different in terms of um, the rather the sequence length is not long enough to differentiate those three, right? So, and you can see that they are all able to predict properly. So now that I have done this and you can see it will be much faster if I switch to a GPU. So I can actually change runtime type to a GPU and it's going to restart everything. And it took a bit of time, but imagine that this will move so much faster with GPU, especially those points where we were having training. Okay, this is going to fail at this point. Um, I don't know why that failed, but yeah, it's going to fail at this point. We'll just continue from here. Okay, it still fails at this point. We'll continue with the next one. Continue. Right. So I just want to show you how much faster it is training with a GPU. Before I even get there, it's already done training. Right. Um, yeah, so when we want to do this visualization, we will have to um, okay. We'll have to detach because it is um, we'll have to take it back to the CPU. So that gives us what we want. The tensor. Okay, the tensor should be CPU first before item. All right, so we have the same problem here as well. Um, Squeeze. It's still a tensor. All right. So you can see how much faster it was with the GPU. I just wanted to show that we were wasting a lot of time waiting for it before. So that's summary of sequence models. When we come in next week, we are going to talk about sequence to sequence. Then I'll also do a bit more hands-on to explain um, this. But I would recommend you to go to PyTorch website and just check these three: GRU, LSTM, and RNN, and how they are used, right? But I'll try to explain what is going on inside them when we come next week. That's it from me.